welcome to the second Berkeley seminar. It's a delight to welcome Angeline Aguinaldo to talk about, give a talk entitled Diary of a Software Engineer Using Categories. Welcome, Angeline. Thank you.
All right. Well, thank you, first of all, for Brendan for inviting me to speak at this seminar. I'm very excited to come to you as an end user of applied category theory. I come from the University of Maryland, College Park. I'm a third-year PhD student, and I'm also a software engineer at the Johns Hopkins University Applied Physics Lab. So I'm kind of coming into the category theory domain from an extremely applied perspective. So I'm hoping that what I say today might give you some insights on how people from engineering might approach the field and how the different phases of learning and the entire learning process. And also I hope to pique your interest a little bit on the ideas that I have about applying category theory to engineering topics. Okay, so I'm going to go over a little bit about myself, provide a background, and describe, as I said, the reflections on my process of learning category theory, describe how it relates to engineering, provide some example applications that I'm considering from my own projects, and maybe give some ideas about how we can apply or how we can improve applied category theory outreach for engineers. So I really wanted to start about me and give you a background about myself so that you have a sense of my perspective when coming into the field. I have a bachelor's in biomedical engineering and a master's in electrical engineering from Drexel University. And what you're seeing on the screen here is just an example of a movie that I had done in my master's research to write image processing algorithms to segment and track cells as they appear in microscopy full motion videos. So I wrote a lot of the image processing algorithms and also the detection algorithms to identify the different values of the fluorescence markers as they were tagged on the particular chemicals present within the cell. And so the objective of this work was to visualize the proliferation of, in this case, two cells as they go through mitosis and as they go through the cell cycle, and see if this pattern was indicative of a particular metastasis, propensity towards metastasis or cancer. Okay, so after I did that, I was hired at the Johns Hopkins University Applied Physics Lab as a software engineer. And a lot of my projects were aimed towards developing software capabilities for analysts and operators from government and scientific domains. So on the left side, you can see that this is an example of a project in which the stakeholders were FEMA and the National Guard. And I developed with a team of 12 other people a software application that ran deep learning algorithms over satellite and airborne imagery. And then the products of this tool were deployed and given to the FEMA analysts to decide what the level of impact was, or the impact that a particular region sustained after a hurricane or a tornado event. And this second example here, I have a little typo, I'm going to correct this, but this is a metagenomic evaluation testing and analysis tool. So this was intended to serve bioinformaticians with the ability to compare metagenomic classifiers when taking a look at metagenomic samples. So metagenomic sample just means that it's an environment or a sample taken from the environment, for example, dirt, and wanting to characterize what are the microorganisms present in that particular sample. Now the issue is that there's a lot of metagenomic classifiers available through different universities and scientific organizations that are kind of optimizing their algorithms, and we want to be able to compare across them and see how their performance for a particular environmental portfolio of interest how it may perform on that portfolio of interest. And the benefit of this is when you have classifiers, you don't really have the resources if you want to forward deploy to a laptop or a particular cell phone if you want to be able to run these classifications. So being able to down select the tools is the appropriate kind of a helpful use case. And I just wanted to highlight a little bit of the tooling that I'm familiar with. And another thing to note is that the Johns Hopkins Applied Physics Lab is one of the major contributors for the COVID Dash. So we do a lot of the data scraping, and particularly the team that I work with does scraping of state and federal websites to be able to identify latest statistics about COVID and its presence in the national space. Okay, so this brings me here. I'm also a third-year PhD student in the computer science department, and I'll talk a little bit about my research interests later in the talk. So with all of that, you might be wondering, how did I get here, standing in front of you at the Topos Institute? And so some of the ideas, as I was going through the process of designing all of these systems and working with teams to kind of suit different user use cases, make sure that our architecture is scalable, the natural thing to do was go to the whiteboard, of course, and talk a little bit about how our design process is going to work. What is our conceptual model about how we intend for this to behave? What is the user model or intended use case of how are they going to interact with the system? So a lot of these are kind of informal pictorial representations. And so these aren't my diagrams, but they're pretty close representations of the way that the initial design process works. And so because a lot of these tools were either having overlapping team members, or maybe I had a hand in the design process, what I found was that we were actually building a lot of the same stuff over and over again. So despite having the different application spaces be in airborne or satellite imagery versus metagenomic data versus cyber network analysis or social media data analysis, there's a lot of common phases or templates that I was trying to follow, because it was me involved and maybe the same team involved. So for example, we might always have an ingestion of the data phase. We have a pre-processing phase, a processing phase, maybe post-processing and kind of collecting all those results, and some way of exporting it to the user, either in a user format or in exportable form. And so these phases that I was observing kind of led me to think that, is there a way to evaluate or characterize the fact that I've actually built the same thing again and again at some level? So maybe the implementation is not exactly the same, but there's at some abstraction level a similarity between the systems that I built. And so what I realized was that I was actually asking the question, or a very mathematical question, which was, across all of these conceptual models and all of these pictures that I perceive as being similar, is there a general pattern that I'm observing across all of these models? And so that's kind of like a little mathematical process that I was undergoing in my head. Something that I found interesting is, as I talk more with you all and talk with the engineers in my community, the engineering and mathematics have kind of opposing objectives. Mathematics, we all kind of start with the same point, where we have this behavioral model or conceptual model about how things are supposed to operate, and then mathematicians take a look to see if there are the general patterns, as I was saying. Whereas engineers take this behavioral model and implement it, or make an instance of that particular model. And so though it seems that they're opposing, I think there's a lot of opportunity to leverage both and kind of build a pathway between the generalization and implementation. Okay, so you may have noticed that in the beginning of the talk, I didn't mention anything related to theoretical mathematics or abstract mathematics. So I have no prior experience in abstract mathematics or even coursework level. I had approached this topic without that. And so, I mean, essentially what you have in front of you is an engineer with experiential experience in software engineering and no theoretical mathematics background, standing in the Topos Institute for Applied Category Theory. So how has it been? I think the natural next question is wondering, well, how did you get here? How's the trip? So the first thing to naturally do when, so the way I got connected with the rest of you is my advisor was listening to my ideas and saying, it sounds like you're interested in interoperability and modularity of systems and trying to formalize that process. So he said, why don't you take a look at category theory? And he was connected to Spencer Brainer and Esran Subramanian over at NIST. And so I kind of got connected with them, and we've been meeting ever since. So for the past 2.5 years, I've been getting my training from the mentorship of Spencer and Esran Subramanian and those along the way. But I've also been relying a lot on self-study and self-resources. So the first thing to do when you're told to say, to look up category theory is to Google it. And the first entry that comes up on Google is NLab, and I'm sure many of you are familiar with this resource. And it's a really, really fantastic documentation of a lot of different constructions in category theory. And so I definitely see the value of having this archive of all of these new discoveries in this domain. But being that I came from having no knowledge in any of these basic symbols, it was definitely an intimidating process. So I'm kind of looking at this and I'm thinking, is he sure that this is where I'm supposed to be? Or am I really in the right place with this? So, all right, so I kept going because I was a little bit persistent. Maybe there's something else. And I encountered these two resources and Bartosz Małyski's YouTube channel and Tide Bradley's Mathema blog. And these are, though I'm calling out these two resources, there's a lot of other resources that develop intuition, but from my perspective, the appeal by Bartosz to programmers is definitely a draw, and he seemed to be empathetic to the programming perspective, so that was really helpful. And then Tide Bradley's blog is very beautifully exposes these constructions through their illustrations. So I think that was another piece that was really helpful. Okay, so I was as I'm going through this process, I'm doing a little bit of research. I'm meeting with Spencer and Sub. One day we were meeting at the University of Maryland, and Spencer showed me string diagrams. So we were trying to work through a problem of making modular robot programs, or a library of robot skills in which we can compose these different skills we want our robot manipulator to do. We want it to be able to open a door, move an object, close a door. So how do we represent this level of modularity with robot programming? And so I was talking with Spencer and Sub, and he started drawing these pictures on the board. So he started drawing boxes, a few lines connecting those boxes. And admittedly, as he was drawing it, he was so excited about the string diagram stuff. And admittedly, I was like, okay, like I know I draw these diagrams all the time. Like these things depend on this thing and this thing. And then he's like, and then you can slide the boxes. You can move them past each other if they have no dependencies. And I'm like, well, that's really cool, but I'm thinking, well, you can redraw it with the box on the other side. And I'm thinking the idea of formalizing a picture was like completely not in my scope of, or even, I wasn't even aware of that possibility. So I'm like, okay, this is really cool. He said, this is a symmetric monoidal category. And I'm like, okay, great, cool. So, all right, so I left that meeting, and I was like, okay, what's a symmetric monoidal category? And I look at the properties and the definition, and I'm like, it's as I spend more time with it, like a couple months, by more time I mean a couple months of looking at this definition, looking at the pictures, trying to draw the pictures and then represent them as these symmetric monoidal categories, I started seeing the process that mathematicians were trying to get at, which is take this instance of a thing and make it precise, like exactly capture what it is that we have drawn on the board or kind of said in a hand wavy type of way. So I thought that was very fascinating. And then I just want to highlight the second resource that I had, which was Paul Sobinsky's GLA, Graphical Linear Algebra blog. He talks a lot about how to compose string diagrams in parallel and serial ways. And so this was extremely helpful in understanding the kind of structure of string diagrams. Okay, so with that, I was pretty bought in already because I was like, okay, see what's happening, and are there other things? Like, are there other things than string diagrams or symmetric modal categories? So then I was brought to these resources. And of course, the 7 Sketches is a great exposition of a bunch of different examples. I was looking at Lavier's conceptual mathematics book and Categories in Computer Science by Walters. And so while these aren't exactly entirely focused on the string diagram aspects or definitions, this really gave me the breadth of what's available in the foundations of category theory. Okay, so now I felt kind of confident. And after looking at all these, I felt like I kind of got what was going on. And so I was like, okay, I can move on to the next level. How do we apply this stuff? How do we make it useful now? And so I highlight these 3 resources here that I kind of use as regular examples when trying to explain this to other engineers, which the first is the Wisniewski and Schnabier's algebraic property graphs. And so when I say, well, there's a formal way that we can combine database schemas or fuse them together, people are like, wow, that's awesome. So, so that's kind of a common example. And then the second one is representing dynamical systems in this kind of graphical syntax. That is extremely fascinating to people, to think that they can take this linear syntax and kind of make pictures out of it, and then it looks really cool, and it exactly captures your system. I think that is a big selling point. And then Andre Sensi's mathematical theory of co-design, in the idea of being able to make templates of your design and then provide instances of those templates, is a very natural way to think. Like it's an intuitive way to approach engineering design, but to think that you can actually capture that in a mathematical way is also another fascinating thing. Okay, so I've gone on this journey. I've taken a look at a lot of resources. What's the hot take on what do I think about category theory? So I wanted to highlight benefits and challenges. So the benefits that I'm finding is, I kind of alluded to it earlier, is that this is an organizational tool. It helps me exactly capture precisely the transformations I'm kind of doing in my head, like by shorthand. So I like if I'm looking at a graph and I'm looking at its nodes, and then I kind of want to pinpoint a specific node, that indexing into that graph, this graph structure or this graph visualization, is exactly captured as transformations, or we can kind of represent those as functors into finset to graph category. Okay, so the next benefit that I'm finding is the graphical syntax. Of course, it's kind of its biggest selling point. Especially the emphasis on making it intuitive. The string diagrams and the wiring diagrams and the port graphs are all things that are very appealing to engineers, as you all probably know. And the third benefit is this, what I call like parallel universes. So the way that I understand functors, and I guess natural transformations as well, is there's 2 categories, and you want to establish a correspondence between these 2 categories, and they may have different objects, different morphisms, but the idea is when you do something in this category, there's an alternate universe in which, when you go through those operations, the same thing will hold in the other universe, and you can kind of do multiple things at once. So this is the way that I try to understand this functor stuff. Okay, so some challenges is that I find it a little bit, for me personally, hard to intuit. So if we, as I said, if we're kind of using, if we're trying to capture the transformations that I'm doing shorthand in my head, I'm obviously not aware of the fact that I'm doing it. So, to have someone pull it out and say, well, you're actually mapping finsets to a different category naturally, and it's a little bit, takes some time to get a hang of it. So that's a little bit that's some of the challenge that I have. I find it a little bit difficult to communicate without special terminology. So the definitions are, the terms are loaded with these properties. And this is kind of with any field. There you have special terms, special acronyms, and things like that. So I kind of get I get that it's terms make it easier to communicate. But to an outsider, monoidal and also morphism is like something that I had been thinking about for a year, and I'm like, what do they mean by morphism? I get now that morphism, like we got homomorphisms, isomorphisms, like those are all things and those are morphisms and stuff. So, so I kind of get the origin, but if you're unfamiliar with the domain, it's like naming is kind of an interesting thing. And then the last thing is I find that it's hard to get it right. And by get it right, I mean take an application and categorify it. So there's a lot of impetus or push to try to categorify things. But as an engineer trying to practice this, I go to Spencer, I say, well, what is this the category? And then is this the functor between those categories? And he'll be like, I don't know if that's really, it's like, it's not quite that. And so there's a whole lot of dialogue of, if I propose that this is the construction, and he kind of will say, well, we also have, or this other category would be more suitable for this. Sorry, I'm being vague, but that's just, that's how that's one of the challenges I see. Okay, so now that I'm kind of bought in and I'm hanging out with all of you, I wanted to identify the things that I've learned from looking at the literature of in applied category theory. So I've decided to consider some basic or classify the results that I see across multiple papers as belonging to some of these classifications. Now, this is not an exhaustive list, and also this is from my perspective. So the lens in which I'm trying to understand this material is, and this is the way that I express it through just identifying classes of different results. But also, it may not be as precise to your liking, so sorry about that. You can ask me or correct me later. Okay, so the first result that I'm getting the sense of is the desire to define new composition operators. So when I think about the operators and the wiring diagrams, I think the value or the new result is that we're not composing things we're composing things in a different way. We're composing the nesting part of the actual the structure, instead of chaining things together like you would with a string diagram. And so the second result that I'm noticing is that we want to show when things are equal to this other thing. So when I think about that, I think about the natural isomorphisms, and given to things, we want to establish a map that'll to prove that those two things are equal to each other. The third result that I'm observing is generally categorifying things to have benefits as compared to existing algorithms. So there was a discussion this morning in the Applied Category Theory Adjoint School where we were talking about what are there algorithmic benefits to categorical representation. And so I think that's a big push that people are trying to do. And I think the example that I have here is the decorated cospans. This may not really make a lot of sense maybe that was not the initial intention, but the way that I see it is the decorated cospans gives you the ability to generalize graph joins, for example. So if we want to join two graphs, instead of kind of concatenating their vertices and edges, we want to join over a specific subset of those common entities within those graphs, but not have to join the entire thing. And so that's kind of the benefit I'm seeing from the decorated cospans. There's also the definition of new graphical syntax. That's another result that I feel like is in the work. So the desire to add more bells and whistles to string diagrams is something that is particular of interest. And then the last thing is to show that things are analogous to another thing. So when I say this, what I'm thinking about is the natural transformations and functors, and saying if we can establish maps that are either loose or completely full, faithful kind of maps, then we can say that two domains or two categories are analogous. All right. So how does this, or how do I see this relate to engineering? I wanted to enumerate some of the common engineering problems that we encounter when actually implementing different capabilities. And the first of which is kind of an obvious one. It's security and safety. I kind of bundle this in with the verification, the term verification. So the question becomes, did I build the product right? And the right part of it is, there's different ways to show that. So if we prove, or if we show that what we built is correct, does it compile, does it run? Those are the kind of things that I'm thinking about. And then also, does it have like an integrity when you're trying to plug in different modules? So if I say, for example, that this system is actually modular, I can actually plug something in with this specific interface, is that really true, or is it just something that I said? So how do we show that? That's kind of one of the problems I think about. The second one is effectiveness, which also is termed as a validation. So did I build the right product? So compared to a desired conceptual model or desired behavior I want the system to have, does my implementation map to, or map exactly to this conceptual model that I'm interested in? Yeah, so I think that's just another question I have. And then another question is efficiency. So can I make this run faster or with fewer computations? That's one's pretty self-explanatory. There's always a desire to make things run in a smaller form factor, require different, fewer or lower memory consumption, and run faster or in parallel. So those are some things. And then there's comprehensibility. So a big piece of engineering is working in teams and having to onboard people and have people understand that the thing that you built and the relationship, the interactions between the different modules. So is there a way to, can I improve my documentation? Can I improve the syntax in which I'm writing it in to improve comprehensibility? And then the last problem is innovation. This is more of a business case, I would say. So inherently in engineering, there's not really, like to engineer a system, you don't really need to be innovative, but in order to compete and kind of exercise creativity, innovation is a big part of it. Okay, so I tried to, you can see that there's some loose alignments with the category theory results and the engineering problems that I had listed. So I'm suggesting that there is some, that these results address some aspects of each of these classes of problems when engineering a system. And I'm going to go into a few examples of that. So the next section is how can I apply category theory? So I'm going to go through this, go through a quick tour of some of the projects that I was working on that I think address some of these engineering problems. They may not necessarily use the particular tooling that I listed on the left, but I find that this is just the way that I'm organizing my projects and kind of considering their value in engineering problems. Okay, so before I go into the examples, I just wanted to list out the framework that I've been observing as when I go through all the exercise of applying category theory. The first step is always to decide the tools. So this is kind of on the category theorists or the mathematicians to decide what are the available toolings based on how they understand the concept. And also just generally communicate the value of each particular construction and how it distinguishes itself from another construction, whether it be more general or more strict. that's kind of on the category theorist expert. The second phase is aligning the application concept. So this is the collaboration between the category theorist and the engineer to say, well, this is my problem and this is how I understand the domain, and it's a dialogue between, like, from what you can hear or from what you hear about the domain, what is the appropriate tool? So these things are kind of iterative, the first and second phase. And then the third phase is how do we encode the model? So how do we actually make this computable or be able to represent it in a salient format? And so this is both, this can be the category theorist, or this can be something like CatLab. I think it's kind of addressing this, or the engineer. How do they choose to represent the CT tools that you've decided on in a computable way? Okay, so then I'm just going to go through some examples here. So the first is this goal-oriented robot programming. And I suggest that this is addressing a security problem with engineering, in that we want to be able to compose different modules with integrity and with guarantees to say that if I were to swap out a module or if I were to chain these modules together, we can be sure to have a correctly constructed program, and it'll run all the way through. So the way that we addressed this was modeled the design of the actual skill library against these modular interfaces, which I represented as symmetric monoidal categories. So we have 3 representations here. The farmost one is I'm considering the physical representation of the robotic arm, and so I say that that is its own category, the actual existence of that robot arm in the physical world. And the resources that it requires is for a particular task, like open the door using the gripper. It requires a door and a gripper. And then there's a functor to another representation, which is the software-based representation of that program. And so that software representation is the different functions that I've implemented in C++ or Python with a particular signature for its arguments and particular return values. And then within there is, within each function is an implementation that calls on the third representation, which is the command, the robot-specific command. So typically what happens is most robotic programming occurs in this kind of last representation, actually sending waypoints, desired waypoints, in order to manipulate the robot and gripper in the desired way. But the idea that there's potential abstractions is still kind of an open area of research. So how do we relate or correspond these abstractions to these low-level commands was the goal of this project. And this was published, or this was accepted into IEEE transactions just last week, actually. Okay, so the other problem that I'm considering is modeling P code for reverse engineering, and P code is just a higher abstraction to assembly opcode. So P code attempts to abstract away the specifics of your operating systems or your hardware, and kind of represent the same opcodes, but with these higher level abstractions. And so I'm suggesting that modeling these low-level programs using category theory might give us benefits in effectiveness, because if we take our compiled binary and take a look to see how it maps to our conceptual model, could we kind of measure or see the difference between our implementation as compared to the intended behavior. And so this is ongoing work with Georgios Bakurtzis, Spencer Brainer, and Eswaran Subramanian. And some of the ideas that we're thinking is potentially using monoids and polynomial functors. Yeah,
Well, why do you want to reverse engineer code?
Why?
Yeah.
Well, I think, so the way that it could come about where you have a compiled binary about maybe your own system and you're trying to reverse engineer it to get a sense of whether it's done whether it's doing what you want it to do. You might have another piece of code that is compiled binary of a system that you don't know anything about, and that's kind of a redocumentation phase for reverse engineering. They want to take a look at the binary and try to figure out what are its modules, or are there modules, and what are these modules doing and how they're passing data.
Is this ultimately for like network security or just like forensics?
Yeah, like forensics, networks. Yeah, I don't know about network security, but forensics may be one of them. Yeah.
Cool.
Yeah. Okay, so the next example is I kind of alluded to earlier, which is a use of decorated cospans for graphs. And in this case, this is an example that I had shown in the Applied Category Theory of Joint School, where we can represent different connection logs of a network. So if we scan a network for all of its transactions that are occurring between machines, and kind of get a sense of what the data is for each one of those transactions, can we represent a graph? Can we join two isolated networks and answer the question of whether these networks or different machines are accessible from a specific IP? So instead of having to join these two networks that I consider to be isolated, however they may have some overlapping machines, we can actually isolate the machine of interest in which we're trying to investigate whether there's a connectivity between these two networks. So can I actually access that blue IP given that I am in this yellow IP, and can I guarantee that I'm actually passing through this red IP? So the decorated cospans was used to join these two, and then you can run a connected component analysis algorithm and guarantee that you actually are passing through this single IP. Okay, and so the next application is around comprehension. So another task in robotic programming is beyond motion planning is task planning. So this is the use of AI planning tools to reason through symbolic logic. So if we have a domain-specific language that describes the actions that are available in this world and the predicates that it needs to satisfy in order to participate in that action, we can run some planning solver and come up with a solution. But the solution that is typically come up with is this kind of opaque list of actions and their parameters or values in which to insert in the parameters. And it's not immediately obvious how these are related to one another. So what are the dependencies or reasons for choosing stack after this pickup? So I use CATLAB to cast these into morphisms and chain them or compose them together as a string diagram. And so this visualization, the benefit of this visualization is, as I said, showing exact causality between this action and this action because of their dependent wires. And so this was accepted at the ICHCAI Generalization and Planning Workshop, which will be presented later in the summer. Okay, and so this last example is kind of in the works. There's no work around this yet, but it's kind of addressing this innovation problem that I was referring to. So can we use the analogies? Can we use category theory to establish analogies between two domains in order to move one domain forward? So I'm suggesting that maybe if we can model these, what we understand in programming languages in a categorical way, and then establish a correspondence with robotic programming, can we move away from having to program very low-level waypoints for manipulating objects and kind of move upwards into application-level programming or kind of higher-level programming. So these, all three of these levels have a lot of experimental or kind of open areas of research. How do we write better robot abstractions? But I'm thinking that we can probably leverage similar structures or organizational systems within each of the programming languages domain to create new insights in robotic programming. Okay, so the last section I have is how can we improve applied category theory outreach. I just have 4 ideas here. I think as we continue to apply the concepts from category theory, especially highlighting the aspects of the problem that help decide the value of the particular categorical tool would be really helpful. So for example, why is the universal state machine example usefully solved by a polynomial functor? I'm sure there's a very good reason for it, but writing it out in papers once this is actually, if this is actually published, is something that would be useful. Categorifying existing engineering abstractions would probably appeal to a lot of engineers. So taking a look at the P code or model-based system engineering and kind of just explain what the categorification of these things are would kind of would help us enter into the field of engineering. This notion of a cognitive versus categorical translation table is something that I thought about when presenting the decorated co-spans for network security. And at least writing it had really helped me understand exactly the cognitive or translation process that was occurring and how it maps to the categorical operation or categorical step that I took. And so I think this would also be beneficial in bridging the gap between those unfamiliar with the categorical terms. The last idea I have is kind of somehow visualize this taxonomy of categories, and especially the relationships about generalizing or restricting. I really like this image from Domain of Science YouTube channel, and he kind of outlines the domains as this really pretty map. Would be really cool to have a similar or maybe a tree structure like visualization of how the different categorical constructions from foundational category to higher category theory relate to one another, and kind of where they are on this bigger map of category theory. Okay. So those are a lot of my ideas. Feel free to provide feedback on how to make things more precise, and feel free to ask questions about any of the examples that I talked about. I just wanted to provide acknowledgement to those who kind of helped me along the way. It's really to the benefit of these conversations that I'm able to even be able to talk about this and apply these things, or attempt to apply them. So thanks for listening. Feel free to, yeah, thank you. Yeah.